Welcome to another podcast. In this episode, we're going to be taking a look at what's called the Beats phenomenon for a undamped harmonic oscillator with forcing term. So the equation that we're going to be taking a look at to start out with here is y double prime plus omega naught squared y equals, and I'm going to have a trigonometric function for the forcing term. And what I want you to take note of is that the natural frequency of the spring is omega naught, and the frequency of what's called the driving term, or the driving frequency, is omega 1. And what we're especially interested in this video and the subsequent videos is what happens as omega naught approaches omega 1. In other words, as the driving frequency gets closer to the natural frequency of the spring, what ends up happening as a result of that. Now, I want to solve for a particular solution here, and I'm going to use exponential response to do it. The book calls this the complex method. So what I would like to do is take and look at the complex equation by making the right-hand side a complex exponential with the same frequency. In so doing, what I have done is I've set y sub p, the answer to the original problem, equal to the real part of this z sub p that I'm trying to find from the complexified equation. So, using the exponential response formula, this particular solution is a e to the I omega 1t divided by the characteristic polynomial evaluated at the root I omega 1. If you work that out a little bit further, the characteristic polynomial here is r squared, so it's I omega 1 squared plus omega naught squared. So this is the characteristic polynomial r squared plus omega naught squared with I omega 1, because that's the frequency here, or the r value for e, plug into it. If you need a review of that, go back and look at, there's at least 2 videos that talk about the importance of this I omega 1 to the process of doing exponential response. We had a couple of videos about that in the last lesson. Alright, so taking this a little bit further, I need to find my particular solution yp by looking at the real part of z sub p. And the real part of z sub p here, if you're looking at this, let me take this out just a little bit further. This is a over I squared is negative 1, so we're going to switch the order here. And then this is times e to the I omega 1t, but that is cosine omega 1t plus I sine omega 1t. And so the real part of this expression will be all the things that are multiplied by, or not multiplied by, an I. And that is the coefficient here times the cosine piece. And so the real part of this solution is a over omega naught squared minus omega 1 squared cosine omega 1t. Alright, because we know from previous experience that the homogeneous solution to this problem is a frequency omega naught, that's why it's called the natural frequency here, cosine omega naught t plus c2 sine omega naught t. This is the homogeneous solution, so if the right-hand side of the differential equation were 0, that would be the solution we'd get, which means that our general solution to this problem is y of x equals y sub h plus y sub p, which is, just writing it all out, c1 cosine omega naught t plus c2 sine omega naught t plus this term here. And notice that it's only in the particular solution where the frequency omega 1 shows up. It doesn't play any role at all in the determining of the cosine omega naught t and the sine omega naught t, but it does play a role in determining C1 and C2. So say, for example, I wanted to find the particular solution when y of 0 equals 0 and y prime of 0 equal to 0. So I'm introducing some initial conditions now. The first initial condition is pretty easy to see, that when y of 0 is 0, you end up with the cosine pieces surviving. So y of 0 is going to be C1 plus a omega naught squared minus omega 1 squared, and that's going to be equal to 0. So the cosine pieces survive, but the sine piece goes away when t is equal to 0. This implies that C1 is going to be negative a over omega naught squared minus omega 1 squared. So we have the first coefficient here. C2 is actually really easy to calculate here, because if you plug C1 into C1 up here and look at taking the derivative, when I take the derivative of this function, the two cosines will now become sines, and the sine will now become a cosine. So since the cosines are becoming sines, when I try to plug 0 into them, they're going to disappear. What that means is, in the derivative, this term and this term won't exist. And so if I look at just what's left, then the derivative evaluated at 0 would be C2 omega naught cosine of omega naught t, and that needs to be equal to 0, and if I plug t equal to 0 into that, you can see that that's going to be 1. I do not want omega naught to be 0, so the only thing that's left to conclude is that C2 must be 0 in that case. What that gives us then is a particular solution of y of x equal to, well, if I get rid of C2, then notice that my C1 looks exactly like the coefficient for the particular solution, and so I can easily combine these to look like a omega naught squared minus omega 1 squared, and then I've got two competing frequencies for the cosines. I've got a cosine of omega 1t and a sine, and a cosine of omega naught t. So we've got the two competing cosines there that have different frequencies. And so what we're really after here is a description of what this thing looks like. So what I'd like to know is, what happens as omega 1 approaches omega naught? See, because this is the solution to that equation, and you can see that when omega 1 equals omega naught, we have an indeterminate form, because I get 0 in the top from this piece and I get 0 in the bottom from this piece. And so the limit is very unclear what's going on there. We're going to address that in the next video, but I'd just like to look graphically at what's happening. So what I've done is created a Maple file, and this is on the blog for you to look at. What I've done is I've taken and looked at a function similar to the one we ended up with there. So rather than type in omega, I used A for omega naught, so this is the natural frequency, and then this is the driving frequency. Actually, I reversed those. So 11 is the natural frequency here, and A is the driving frequency, and I want to look at what happens as A approaches 11. Now, to do that, I've created this animation, and I want to explain a little bit about what's going on here. So I'm plotting that function from minus 8 pi to 8 pi, and from y from minus 0.3 to 0.3, just so we can see everything. But I'm plotting it for different values of a. So there's going to be a plot that happens in sequence. So it's going to show me, it's sort of animating this by showing me the next plot in the sequence for different values of a. And basically what I've done is I've iterated at 0.01, so I'm starting with an a of 1/10 that, which is or 1/100th of that, which is 6, and I'm going to end up with an A that's 10.99. So I wanted to look at the range of values for this limit as A goes from 6 up to 10.99, almost to 11. So this is what this animation is showing, and if I run it forward a little bit here, you can see that what ends up happening is as we get closer to 11, it doesn't look like much is happening, but all of a sudden, the closer we get, things start to sort of coalesce into these little groupings. These little groupings of a large frequency on the outside, so we've got this large band frequency occurring, and then in between we've got these shorter wave frequencies that are occurring. And this becomes really prominent the closer we get. So for example here, this is frame number 400. So if you add 400 to 600, we're at 1,000, and 1,000 would be a frequency of 10. So we're at a frequency of 10 where 11 is the natural frequency, and you get this really pronounced grouping where you've got one long frequency and a short frequencies in between each little sort of half period here. This is what's called the Beats phenomenon. The Beats phenomenon can be heard really well anytime you tune a guitar or something like that, or you play a musical instrument. You actually listen for the beat sound to know that you're getting really, really close to the resonant sound that you want. And we'll talk more about resonance in another video. But what ends up happening is we keep getting closer, these outer oscillations, these outer frequencies become more pronounced, and the amplitudes thereby increase, and we push it really, really far. So here we're at 475, so this would be a frequency of 10.75. You can see we still have the beats, but the amplitudes are getting bigger, and if we push it too far, if we push it all the way, we basically get an uncontrolled amplitude in our response. So the idea here is, going back to what we talked about before, is this is indeed the solution to the problem at rest. So this is what happens sort of in the steady state for the problem at rest. There's nothing initially that's starting the problem, but the idea is if we drive this system, try to drive this system with a frequency that's very close to the natural frequency of the spring, it reinforces the motion so that the amplitude term here gets larger and larger. Now we're going to look at this in more detail in the next video, but I wanted to introduce the Beats phenomenon to you in this one. So thank you for watching.